Hello everyone, this is Teng. I'm from Electronic Arts Data and AI department. Our department actively look for big data solutions, such as high performance data platforms, natural language processing, or a computer vision. Today, I'm here to show you how we build high performance platforms on AWS to support real-time gaming services. And the platform here is specifically Presto and Alluxio. These are the popular games that our company produces. When the users are playing, the user's actions or in-game events will become data and uploaded into our system. And the raw data, the volume of raw data could be petabytes. And then later on, our producers, marketing, data analysts will rely on this data to understand our customers and better serve our players. Our department kind of sits in the between. So it's our job to convert the raw data into structured data to be more analyzable. This is the system that we're currently using. It's basically a tech deck based on Hadoop echo environment. The raw data comes into the system every 1 or 2 minutes, depends on the game, and Hadoop pipelines download and merge the data, and then later on ETL jobs such as Hive ETL pipelines will merge the data and construct them into table formats. This system has been running stable in our company for a while and widely adopted by many companies. But recently we noticed that it's not supporting real-time services very well. Because this pipeline is good for batch processing, but there is a big overhead, a processing overhead for real-time service. And also every piece of data has a predefined lifecycle, so it's difficult to retrieve the data in the middle. And in this system, for the system, it's difficult to integrate with the current BI tools. Then we need to develop a new system, the next generation of data platform to support our real-time gaming services. Next, I will introduce 3 typical types of real-time services we're using in the company. First is the data insight, analytics, and visualization tools, such as Tableau or Dandas. Second type is the real-time dashboarding, such as Superset. A third type is the conversational chatbot, such as Slackbot. So let's take a closer look at the requirement of each use case. First use case, the data insight, analytics, and visualization. For example, typical tools would be Tableau or Dandas. For these tools are usually in the backend, they're connected with many data resources, many different data storage. And the analysts, when they're using these tools, they download the data from many endpoints. Then they apply different algorithms on it, visualize the data, and then dig the knowledge from the visualization. To support this use case better, we need the new platform to be able to cache the data temporarily. And we need a faster computation engine to provide instant data visualization. The second use case is the dashboarding. For example, Superset or Prometheus. We currently use dashboard to monitor many things, such as game KPI or even the system health. Dashboard usually needs to connect to many data resources. They need to combine the data into one graph, and more importantly, it refreshes very short period of time. To support dashboarding better, we need the new platform to have a stable data caching layer, and we need the computational engine to be faster to support the frequent refresh. Our third use case is the inside chatbot. For example, we have Slack chatbot and many other chatting bots. This chatbot in the backend, usually they're connected with many data resources, and the users can ask questions through them directly. The chatbot needs to respond immediately. To support a chatting bot, to better support our chatbot, the new system needs to have a temporary data caching layer. And similar to the monitoring case, The chatbot needs a fast computation. It has to respond immediately. For our next generation of high-performance platform to support the real-time services, many enterprise platforms such as Redshift or Snowflake can perform very well. But however, these tools usually have very high cost. So we need a new platform with similar performance but much lower cost. Then we investigate the integration of Presto and Alluxio, with Presto as the computational engine and Alluxio as the caching layer. For the new system, our architect design is very simple. All the data will be stored on S3. Then we mount Alluxio on top of S3 as the caching layer. Then we use Presto to retrieve data from Alluxio directly. In our experiment, we use 3 AWS H1A XLarge instances, and each one has enough ephemeral disk mounted on it. Each instance, we have one instance working as Presto coordinator and Alluxio master, and all the 3 instances have worker and have worker services on it. We mount Alluxio on top of S3, and we configured 2 catalogs on Presto. One is pointing, for one, all the tables are pointing directly to S3. And for the other one, the data is pointing to Alluxio directly. So later on, we can compare the performance of these 2 catalogs. And for Alluxio, we preload all the same data on S3 into Alluxio with the distributed load command. We use 4 independent benchmarks to evaluate the performance with or without Alluxio. At the beginning, we noticed that Alluxio outperforms S3 in many benchmarks, but it's not very good at processing large amounts of small files. To tune the performance, we later on enabled the metadata caching, and we noticed that in this case, Alluxio outperforms in all of the cases. Next, I will introduce the 4 datasets that we use and the result that we get. The test 1 is our internal benchmark, which is the real queries of our production system. It shows the analysis of the players in in-game events. All the data sets are in ORC formats in different sizes, 1 or 10 or 100 gigabytes. The query we use is select all the columns from the test table with a simple filter, which is typically an IO-heavy query. And as the result, we can see that Alluxio, with the metadata caching enabled, can outperform S3 up to 7 times. The second test that we use, and the rest 3 tests, test 2, 3, and 4, are the simulation of the previous 3 use cases. Test 2 is a simulation of the data visualization case. All the queries are retrieved from our production system and with real data sets. We use 2 commonly used data sets and queries from Tableau and Dandas. The query is simply select all from the test table with a filter, group by, and order by. So we are simulating both CPU and IO-heavy queries. We did not enable any metadata caching in this case because we already seen the performance improvement. Presto with Alluxio is 2 times faster than S3 and 5 times faster for the Tableau datasets. The third test is simulating the dashboard use case. In this use case, we created many small files. Every file is about 2 megabytes in the size, and totally we tested 50 files, 500 or 5,000. And the query is simply a selecting and aggregate all of them by dates. Without metadata caching enabled, we notice the Alluxio performance is similar to S3, but when we enable enable the metadata caching, Alluxio could be up to 5.9 times faster than S3, which means that enabled metadata caching can reduce the execution time significantly. The metadata caching could memorize the hot data and the metadata of the file, which can save lots of time during the processing. The last case is simulating our conversational chatbot. The dataset we use is a snapshot of the daily game performance, and the query is simply select and a hyperlog log from the test table with a simple filter. It is typically a CPU-intensive query. For this one, we have this one has the biggest performance improvement. The time even without metadata caching, the running time shorts from 85 seconds directly to 3 seconds, which is about 27 times faster than S3. In a conclusion, we can see that in all the cases, Presto plus Alluxio can outperform S3 significantly. And we also see that when handling large numbers of small files, Alluxio with metadata caching enabled can have performance improvement better than without it enabling. And for the future work, we wanted to do more investigation on this caching mechanism. We want to see how it recognizes hot or cold data, how it increased the replica of the hot data, and this will be helpful for us to tune the system for better performance.